For decades, scientists have been almost certain there's water ice buried inside the moon's darkest craters. But knowing it's probably there and knowing exactly where to dig are two very different problems. Drilling blind is slow, expensive, and it's easy to miss the deposit entirely. A study published on July 31, 2026, in the journal Science Advances proposes something different. Instead of digging for the ice, listen for it. Researchers at the University of Maryland, Lawrence Berkeley National Laboratory, and the University of Hawaii say that moonquakes, the moon's version of earthquakes, might be the key. Here's how that's supposed to work, and why the timing of this discovery could not be better. To understand why this matters, you need to understand what makes the lunar poles so different from the rest of the moon. Because the moon's axis is barely tilted, sunlight grazes the poles at an extremely low angle. Inside the deepest craters near the South Pole, that means some floors have not seen direct sunlight in billions of years. Temperatures inside those permanently shadowed regions can drop low enough to trap water and other volatile compounds almost indefinitely. Scientists have had indirect evidence of ice there for years. Orbital data, neutron spectrometry, hints from radar, each pointing toward the same general conclusion without ever pinning down exact locations or quantities. What nobody has done is directly measure it. And that gap matters, because NASA's Artemis program is targeting crewed landings in the South Polar region as early as 2028, specifically because of that suspected ice. Water ice isn't just a curiosity. It's arguably the single most valuable resource a future lunar base could have. Melted and purified, it becomes drinking water. Split apart with electricity, it produces oxygen to breathe and hydrogen for rocket fuel. In practical terms, a reliable local source of ice means future missions don't have to haul every drop of water from Earth. And that changes the entire cost equation of a sustained human presence on the moon. So the incentive to find precise ice deposits, not just a general probably here zone, is enormous. Here's where the moonquakes come in. Moonquakes are real. The moon is seismically active, just far less dramatically than Earth. They're caused by things like meteorite impacts, temperature swings that crack rock, and slow tidal stress from Earth's gravity. When a moonquake happens, it sends seismic waves rippling outward, the same physical principle as an earthquake here on Earth. The research team ran computer models simulating how those seismic waves travel through lunar soil, first through dry regolith, then through regolith with ice mixed in at different depths. What they found was consistent. Buried ice changes the seismic signal in a distinct, recognizable way. The waves move differently, roughly 2 to 3 times faster through icy soil than through dry soil, according to the modeling. That difference is large enough to act like a signature. Something you could, in principle, detect from a distance without ever touching the ground where the ice sits. According to the study, this method could potentially map ice buried as deep as around 800 meters below the surface, far beyond what any drill sent to the moon has attempted so far. This wasn't purely theoretical. Researchers at Berkeley Lab used a specialized cryogenic chamber, nicknamed Frost, to physically test how real icy soil samples behave under lunar-like conditions. Comparing that ground truth data against what the computer models predicted, the two lined up. That's an important detail, because a model that only works on paper isn't very useful to a mission planner deciding where to land a seismometer. The modeling wasn't a single simple prediction either. The team ran simulations across a range of variables that actual lunar ice deposits could plausibly have. Different depths, different concentrations of ice mixed into the regolith, and different layering patterns, since nobody actually knows in advance whether buried ice sits in one solid layer or scattered unevenly through the soil like frost mixed into gravel. Across that whole range of scenarios, the seismic signature held up as a reasonably consistent detectable pattern, rather than something that only worked under one narrow, best-case setup. That robustness matters, because a real seismometer landing on the moon won't get to choose a convenient textbook version of the ice deposit underneath it. There's also a reason this technique could end up mattering well beyond the moon. Permanently shadowed craters aren't unique to Earth's satellite. Mercury, despite orbiting closest to the sun, has its own permanently shadowed polar craters that are cold enough to host water ice, confirmed by radar data decades ago. Any seismic prospecting method proven out on the moon becomes a plausible tool for future missions to Mercury's poles as well, and potentially other airless, geologically quiet worlds where drilling blind would be just as impractical as it is here. Here's what makes this story different from a typical "new study suggests" piece. The prediction is about to be tested in real time. China's Chang'e 7 mission is expected to launch as early as late August 2026, essentially now, carrying a seismometer as part of its instrument package, with a landing targeted near Shackleton Crater, one of the regions with the strongest suspected ice signatures. That means researchers may not have to wait years to find out if their model holds up against real lunar data. NASA has its own version of this test coming too, a seismic instrument called the Lunar Environmental Monitoring Station, which Artemis astronauts could deploy on the surface as early as 2028. In other words, this isn't a discovery that gets filed away for a decade. Within the next few years, and possibly within months, we could know whether listening to the moon actually works as a prospecting tool. There's a bigger reason this matters beyond fuel and drinking water. Ice trapped inside permanently shadowed craters may have sat there, largely undisturbed, for roughly 4 billion years, dating back to some of the earliest chapters of the solar system's history. That makes it a kind of frozen record, chemically sealed away in darkness since before Earth's own oceans had fully settled into place. Studying its composition could tell us something about how water was originally delivered to the inner solar system, whether by comets, water-rich asteroids, or some combination of both, and by extension, offer clues about how Earth's own oceans came to exist in the first place. So depending on how you look at it, this is either a resource prospecting story or an origins of water in the solar system story. It's honestly both. It's worth being clear about what this study is and isn't. This is a predictive model, not a direct detection. Nobody has physically measured buried lunar ice using this seismic method yet. That confirmation depends entirely on upcoming missions actually carrying the right instruments to the right places and returning usable data. The lead researcher on the study has acknowledged as much, describing this work as laying the groundwork for measurements that are still a couple of years away. So treat this as a strong, well-tested hypothesis, heading into its first real-world exam, not a settled fact. If Chang'e 7's seismometer picks up the kind of signal this team predicted, it would be the first real confirmation that we can map lunar ice without drilling a single hole. And it would hand Artemis planners a genuinely practical tool for choosing where to land. If it doesn't match, that's just as informative, because it means the model needs rework before anyone bets a mission on it. Either way, We're going to know a lot more within the next couple of years than we do right now. And the answer will shape exactly where astronauts end up walking on the moon's surface. Beyond what you can see, but never beyond what you can understand. Subscribe and check out the rest of the channel. New episodes on space, physics, and the edges of what we understand, with new content going up every day.